explained to Naomi, we have a challenge with electricity. Indeed, I had even to go to my neighbor's place to ask for assistance. But at least we are here. We are 23. I don't know what's happening, why the others are logging very slowly. We should be at least more than 30, but we will start because everybody is aware we are supposed to have a class. So last time we were looking at the acetic acid derivatives, no, phenamides. I think we were looking at the phenamides, and we gave examples of the phenamides. We gave, of course, mecrophenamic acid, we gave mefenamic acid and flufenamic acid. We also did discuss the importance of stereochemistry in the activity of these drugs. And we did say the two rings which represent the two hydrophobic parts of the COX enzyme or the arachidonic acid, and they cannot be in the same plane. We also did discuss that the amino group or the nitrogen which joins these two non-complanar rings must also be present, necessary for activity. We also did discuss the importance of the carboxylic group, that it is the position of the carboxylic group rather than the presence of the carboxylic group that is important for activity. We did mention you can replace that carboxylic acid with tetrazole with retention of activity. Then of importance for us to remember is that when you have two ortho substituents in the second ring, the two other substituents help to swing the second ring out of coplanarity. I think the last thing we were discussing, where there was a bit of controversy, is the metabolism of mecrophenamic acid. And we did mention, as I had mentioned, that the halogens decrease the metabolic rate of these rings. But we also do need to understand that the amino group has a positive contributory factor. When you have this amino group, if this ring was on its own without an, if it was just a phenyl ring which is halogen substituted, then it's very difficult for it to undergo metabolism. But because of this amino group, which is in the middle and joining the two rings, as I had said earlier, the amino group is an ortho-para director. And because it's an ortho-para director, that means it increases the concentrations of electrons at the ortho position and the para position. That implies that this compound or this ring, if it were to undergo metabolism, it can undergo metabolism at the ortho position, the para position, because in those positions, because of the resonance or the electrons, the lone pair of electrons on nitrogen, which are pushed into the rings, the ortho position is electron rich and the para position is electron rich. And that is why we did see the metabolites which we saw when we were looking at mecrophenamic acid. So indeed there's no real mistake there. All we are saying is because of this amino group, the amino group increases the density of electrons within the halogen, and in increasing the density of electrons, we'll have a higher concentration of electrons at this position here, which is para, and that is 1, 2, 3, 4. At 4 prime, you will have a high concentration of electrons. And also this, when in relationship to the other ring, again, it will increase electrons in this is the ortho position meta para, which is position number 5. And that is why we were able to see that you can get the 4' hydroxyl group, you can get the 4' 5 hydroxyl, and that is because of the fact that we do have this amino group which is increasing the electron density. We also did mention that you do have regioselective metabolism of the methyl group. So this methyl group can undergo oxidative hydroxylation to give us the hydroxyl methyl group, which again can undergo further hydroxylation of further oxidation to give us the carboxylic group. So again, I'm just mentioning, yes, you can get a hydroxyl group at that position. You can get hydroxyl position. This is well explained by the presence of the amino group, which is an ortho-para director. And when we say it's an ortho-para director, it means it increases the density of electrons at the other position and at the para position. I hope that is clear. And I think with that as a reminder, of course, we are saying, we did mention mecrophenamic acid compared to flufenamic acid, compared to mefenamic acid. Mecrophenamic acid has much higher potency. We did because of the two ortho chloro group, one at 2', the other one at 6', and they are very important in flipping or in making sure that this second ring is completely out of planar. with the first ring, and once that happens, then of course you will have the best fit for the receptor. Do please also remember that we did mention you can't substitute the second ring. We can't have substitution in the second ring, but the anthranilic ring substitution of the anthranilic ring renders the drug inactive. And I think that is just a reminder of what how we finished last time. And now I think I want us to move on to the next class. And the next class of drugs is the aryl arachidonic acid. Just note this name, there is no complex, it's not complex. We are saying aryl arachidonic acid. Aryl meaning you will have an aromatic ring. Arachidonic meaning there will be an noic meaning, of course, it's an acid. And you can see that is the noic, this is the arcyl, and that is the aryl. So R being either a methyl or a hydrogen. When R is a methyl, it gives us the propionic acid derivatives. When R is a hydrogen, it gives us the acetic acid derivatives. Then we are saying AR can either be an aromatic ring, like when we look at some of the drugs like phenol, like diclofenac, you find that AR is an AR can be a heterocyclic ring, like when we look at drugs like indomethacin, etodorac, and so on. This is indeed a heterocyclic ring. So I hope you understand this structure. This structure is a general structure for both the acetic acid derivatives and the propionic acid derivatives. It is R that will determine whether we are talking about an acetic acid or a propionic acid derivative. Of course, the mode of action is similar to whatever to all the other mode of action of the non-steroidals. It will block the COX-1, COX-2 enzymes, and of course inhibit or prevent the enzymes from binding to arachidonic acid, and therefore block conversion of arachidonic acid into the prostaglandins, which are responsible for pain, fever, and inflammation. Then now we want first of all to look at the aryl and heteroaryl acetic acid. Please remember, I have explained, it is aryl when the AR is just a phenyl ring or an unsubstituted aromatic ring. It is it is when that group also has a heteroatom like nitrogen and oxygen and so on. So that's the only difference. That's acetic acid, because our substitution up there, of course, with the exception of a few compounds like etodorac and ketorolac, then you find that the R, the substituent which we looked at, I believe it was the R, this R is actually a hydrogen and therefore acetic acid derivatives. Let us look at the general structure and chemistry. And we are saying that, of course, they are derivatives, but the substituent at position 2 is a heterocycle or related carbon cycle. That is simple. We are saying they are acetic acid derivatives. So which means this R is a hydrogen, and we can call this position 2 starting from here. That is 2. So we are saying this substituent AR on carbon 2 is either a carbocyclic group whereby all the atoms are carbon, or it's a heterocyclic group been replaced with a heteroatom with retention of activity. This does not significantly affect the acidic properties of these compounds. So we are saying whether it is a it's a heterocycle, or whether it is a carbocyclic group, that does not have much effect on acidic properties. Remember, we do require the acidic properties. We do require the anion, which will bind the arginine or guanidine moiety within the enzyme. The heteroacetic acid acetic acid derivatives, or when we look at the acetic acid derivatives, we can further divide them into about 4 subclasses. We do have what we call the indo-indene derivative. Indo is like indomethacin. Indene is like sulidac. We have the pyrrole derivatives, and for the pyrrole derivatives, we do have tometin. We do have, I think we have tometin, and I believe in that class also we do have ketorolac. Then we have the oxazoles, and the oxazole is where you have oxaprozine, and then also we do have one class I didn't put here, which is a phenyl acetic acid derivative, where we have diclofenac acid. And I think we can look at those examples. Let us look at those examples in your printout. Let's look at page. So go to page 9. Go to page 9, please. You go to page 9, and you at the bottom, page 9 at the bottom, you can see we have there is indene and indoacetic acids. Remember, this classification is based on the heterocyclic ring. Is it an indene? Is it an indo? Is it a pyro? When you look at Sulidac, you can see that's an indene ring. The indene ring is that ring minus. You can see it doesn't have a nitrogen. So if you compare the ring that is found in Sulidac and that which is found in indomethacin, you see two major nitrogen of indomethacin has been replaced with a carbon, and then the bond between the nitrogen and the next carbon is actually a single bond for indomethacin, but for Sulidac it is a double bond. So that is the indene, that ring which is a phenyl ring, fused to a phenyl ring fused to a cyclopentene ring. That gives us the indene. Whereas if you look at the indo is where you have a phenyl ring, of course, attached to a pyro ring and the tension of activity. So that is the first category: indomethacin, indo ring, Sulidac, indene. And then if you look at, and also if you look at a Todorac, you will also see a Todorac also as an example of an indo derivative. So those are the three examples we'll give for the first one, indene and indoacetic acid. Look for the structure of tometin. It is on page 12. Go to page 12. Now here, of course, the structure is a bit different. You find, unlike in the other compounds where the nitrogen is not attached, where the nitrogen is attached to another ring, if you look at your indomethacin, you find that the nitrogen is attached to the second ring. It was page. It was page 9. If you look at your indomethacin, the nitrogen within the indo ring is attached to the second hydrophobic group. But if you look at now the tometin, there is an L there, tometin, the nitrogen is attached to a methyl group, and the second aromatic ring comes from a different position within that ring. But what we are looking at is that first. We are looking at the first hydrophobic group. It's a pyrrole. A pyrrole is where you have a 5-membered ring, 5 aromatic, 5 the nitrogen as part of as a heterocyclic atom. And if you look at tometin, you can see what we are talking about. Look at where the carboxylic group is separated from the first hydrophobic group with a methyl group. So that's an acetic acid derivative. Also look for that is tometin. Look for ketorolac. Look for ketorolac. Look for ketorolac. So on which page? If you get it before me, you will also see. Look for ketorolac. Yes, look for ketorolac on page 11. Again, if you look at ketorolac, it looks a bit complicated because the first, again, very similar to the other drugs we are looking at. But if you look at where the second hydrophobic ring comes from, you can see that ring, again, is a pyro ring. That ring is a pyro ring, and that's why we are saying ketorolac is a pyro derivative. That ring and the ring, in fact, they are adjacent to each other with tometin. Then you find they share the same. Again, if you look at ketorolac, as we had said earlier, see where your carbon, the first carbon, is the carboxylic group is. From the carboxylic group, whichever way you go, you will see the carboxylic group is separated from the first hydrophobic group with 2 carbon atoms. And that is where we said there is a difference. And that's why ketorolac is classified as a non-classic, non-steroidal anti-inflammatory. It is separated by 2 carbon atoms. Remember, we had said for maximum activity, you require separation the one carbon atom. So you can look for the other drug, which is next to tometin. You can look for zomepirac. Zomepirac is also a pyrrole. Zomepirac, which is very much connected or very similar. Even if I don't have, perhaps you have drawn it, that zomepirac also very similar to tometin. Again, it is a pyrrole derivative. Now, if you look at the oxazoles, look for oxaprozin. That's oxaprozin. Oxaprozin on page 13. Again, now if you look at the oxaprozin, our heterocyclic ring, the ring that is attached to the carboxyl, the carbon attached to the carboxylic group is our ring of interest. If you look at oxaprozin, you find that's an oxazole. An oxazole is, again, 5-membered aromatic ring containing an oxygen and nitrogen separated by a carbon to each other. When they're adjacent to each other, then that's it's isoxazole. Adjacent to each other is isoxazole. When they are separated by one carbon atom is oxazole. So again, oxaprozin is an example of an oxazole. Then also look for diclofenac. Look for diclofenac. And I think diclofenac, which is also there. Diclofenac, again, go to page 14. Go to page 14 of your handout. Then now again, diclofenac boros from the phenamate or the anthranilic acid derivatives, but its ring is not an anthranilic acid derivative, because an anthranilic or anthranilic acid is when the carboxylic acid is directly attached to the phenyl ring. But in this one, you can see this drug is an acetic acid derivative because the carboxylic group is separated from the first hydrophobic group. So kindly note, although they share in terms of that the two hydrophobic rings are separated by amino group, similarly with the phenamate, there is a much difference in that diclofenac is actually a phenyl acetic acid derivative. It is not a phenamate, it's not an anthranilic acid derivative, because the carboxylic acid is separated by one carbon atom from the first hydrophobic group, putting it in its node class. So that's how we get the 4 classes, the indomethacin, and also solidac, the pyrroles, where we have talked about the tometin and the ketorolac, and then, of course, the oxazole, where we have oxaprozin, and the phenyl acetic acid derivatives, where we have the diclofenac. Is there any question up to there? Any question, class? Any question? If there is no question, then we move on. So now we are looking at indomethacin, and quite a number of drugs, they are synthesized from that some of the endogenous molecules do have certain activities. Like for indomethacin, it was synthesized because it was found that the endogenous compound serotonin was found to which contains an endonuclease, is a potential mediator of inflammation. So serotonin, which has an endo ring, is a potential mediator of inflammation. So all they did is that they did some structural modification on serotonin to see whether they could be able to come with a post-inflammation. Because remember, these drugs are non-steroidal anti-inflammatories. It is supposed to oppose to antagonize the activity of serotonin. And that is why serotonin and indomethacin have some structural similarity in terms of their endo ring, but of course the structure is a bit different. The structure of indomethacin is more bulkier, so that when the indomethacin binds the receptor, it is not an agonist, but it is an antagonist. The endo system and the phenyl ring are separated by one atom, and if you look at it, look at the structure again of indomethacin, it is very clear. You look at the structure of indomethacin again, I think it was page 9. If you look at the structure of indomethacin, it fits in that class. Acetic acid, heterocyclic acetic acid derivative, the carboxylic group separated from the first hydrophobic area with one carbon atom. Remember, we said increase on that side. Again, now you go to the general SAR. If you increase, again, exception of ketorolac and etodolac, then you will have a decrease in activity. Theoretically, it could exist in millions of conformations, That all we are saying. If you look at indomethacin, the nitrogen and the carbonyl group. If you look at the second ring, which we can call the chloro-benzoyl group. The second ring, the second hydrophobic group, it has a para-chloro-benzoyl because of the carbonyl group. Going to the nitrogen with a single bond. And you know, molecules that are bound with a single bond, there is rotation around single bonds. And that's why we are saying that indomethacin can exist in very many conformations. But then it was found, as we are going to see, only only one of those conformers has maximum or optimal activity. So we are saying the indomethacin can exist in many conformations, but only one of those conformations have maximum activity. Also, if you look at that compound, you'll see that there is a carbonyl group. That carbonyl group, because the carbonyl group has a double bond. Remember, double bonds are known to restrict movement. So because of that double bond, that carbon in the middle over there, which is attached to a carbonyl group, to an oxygen, carbonyl oxygen, can allows this molecule to exhibit geometric isomerism. It allows it to exhibit geometric isomerism. So we will see that there's a trans conformer. So you're seeing the partial double bond character of the amide restricts rotation. That partial bond, we are calling it a partial bond. It's not a complete double bond as between a carbon and a carbon, but because of that presence of that double bond, there is restriction of movement, and therefore indomethacin can exhibit geometrical isomerism where you have both the cis and the trans isomer. The 2-methyl provides steric hydrons favoring the active conformer, and the hydrogen atom is position 7 and 2' provide hydrons and coplanarity. Again, what are we saying? If that structure, please make a correction of indomethacin at position number 2 next to the nitrogen, put a methyl group. That is position 2. There is a methyl group. All we are saying is that methyl group, because it's quite big, it brings about steric hydrons and pushes the benzoyl, the chlorobenzyl moiety to the other side, so that the chlorobenzyl moiety is cis to the methoxy group. Look at the methoxy group at position number 5, you have a methoxy group. At position number 2, you have a methyl group. So all we are saying is that methyl group at position 2 of the indomethacin pushes the chlorobenzyl moiety towards the methoxy group, and therefore the chlorobenzyl moiety and the methoxy group are actually cis to each other, and that conformation is the one responsible for maximum activity. Again, if you look at position number 7, numbering is from nitrogen number 1. So the nitrogen carries number 1. So when we number them, when we number the indomethacin, we're starting from there. Number 1, number 2, number 3. Usually jump intersection. Number 5, number 6, number 7, and number 8. So if you look at, so that is number 1, number 2, 3, 4, 5, 6. Sorry. 7. That's what I couldn't understand. So you have this hydrogen there at that position. You have that hydrogen and you have that methyl. So these groups allow this compound to allow for the proper conformer to be formed. So there you have a methyl group, and there you do have a hydrogen. And again, we have also talked about that partial bond. So if you look at what we are talking about here, you can have these two conformers. You can have where this methyl group is bringing out, this methyl group is responsible for pushing, there's the chlorobenzyl moiety here, pushing it to be cis, that group and that group cis, they are on the same side. So that methyl group is responsible for pushing this group cis to that, and of course, this double bond here, because of this double bond, there is existence of, there is rigidity, and we can have either the cis or trans conformer. The trans conformer facing on this side, and the conformer that was found to have maximum activity is the cis conformer, as we are going to see. So we are saying, therefore, 2-methyl provides steric hydrants favoring the active conformer, and the hydrogen and atoms as position number 7 and 2' provide hydrants to
Yes.
Yes,
I'm
okay.
fine. All is well. I didn't hear back from Gary, no. Okay. Please follow up with Marsha. Yes. Really appreciate if you can get this done today. Okay, I'm doing that, and I'm sure you saw the trail of emails. I did, I appreciate that. Yeah. So let me see what she says today. Sounds good. Yeah. I mean, they're preferred before you. Most people are unavailable last. Oh, yeah, today. Okay. Right.
Thanks a lot.
Okay, okay.
Back. So we continue with the structure of idomethazine, structure and actions.